Hey guys, we're looking at lesson 4, solving equations with logarithmic functions. We're going to look at several things today. The Richter scale model measures the magnitude of an earthquake, where A is the amplitude in micrometers and T is the period of the seismic wave in seconds, and B is the dampening of the seismic wave as the distance from the epicenter. We're also going to look at the pH scale that measures how acidic or how basic a substance ranks. That scale ranges from 0 to 14, where 7 represents neutral, and each whole pH value below 7 is 10 times more acidic than the next higher value. And then also Newton's law of cooling, the temperature of an object at some time t, where the temperature is the surrounding medium, and T sub 0 is the initial temperature of the object, is given by this crazy looking formula. Now, one of the things we need to remind ourselves of is that some log equations can be solved by changing them to exponential form and vice versa. And we've already seen earlier that if you have an exponential function and it's equal to another exponential function, as long as you can get the bases to be the same, then the powers are equal. And the same would go for logarithms. If you have a log of one base equal to a log of the same base, then the arguments are equal. If the bases are the same, the powers are equal. If the logs are the same, then the numbers are equal. So we'll start off here with an exponential function, and I want to divide by 24 first of all. So 6 divides 24 4 times, and then my trick would be to rewrite 1/4 as a power where the base is a half. So if we had the half base on the left, we could have a half base on the right, which would mean this would have to be squared. So when the bases are the same, the exponents are equal. That means 1/3 of an x is equal to 2, so x is equal to 6. And we have solved using those properties of exponents. In this case, I need to get to the variable, and the variables happen to be in raised to a power. So the way to get them down from the power is to take the log of both sides. And since the base was e, I'm going to choose to take the natural log of both sides. That way we can use the properties of logarithms and bring that x out in front of natural log of e, and do the same thing with the 1 plus x. We can bring that entire power out in front of natural log of pi. Now remember, pi's a constant, it's not a variable. So we're going to have to solve for x. The natural log of e is 1, so on the left side of our equation, we're just left with x. And then using or applying the distributive property twice here, we've got 1 times natural log of pi plus x times natural log of pi. And our job is to get the x terms together. So x minus x natural log pi is equal to natural log pi. And then by factoring out x from both of those terms, we could divide. And if we needed the exact answer, we would be finished. But I think it would make more sense if we could go to a calculator here and get a decimal approximation. So we want natural log of pi divided by the quantity 1 minus natural log of pi. So let's see how that looks. The natural log of pi divided by 1 minus the natural log of pi. Oh, 1 minus, that didn't go very well. There we go. So about negative 7.909. The power negative 7.909. And we could go back and check this, and those would be really close to each other. So let's give that a go. E to the negative 7.90942 is about 0.000367. And then taking pi and raising that to the 1 minus 7.90942. You should get really close to that decimal answer. Uh-oh, I got a mess here. Okay, there we go. Nope, that didn't work. Pi to the, oh, not times. We need pi, raised it. We're going to do pi and raise that to the 1 minus 7.90942 power. And how close are we there? 7, nope, that's not that close, is it? 0.000367. So they're close, but not too close. This one's 3 zeros and a 3, and this is 3 zeros and a 1. So we're off by a little bit. We could use the solve feature. When is e to the x equal to pi raised to the 1 plus x power, comma, x, we're solving for x, and negative, okay. And that's about the answer we got, so 7.909. That's as close as we're getting on that one. In example 3, we have a quadratic type, and we're going to support our answer graphically. So can you see that it looks like an x squared here and a 3x here and a minus 4? We're going to think about e to the x times e to the x is e to the 2x. So using that thought process, we want factors of 4 that add up to negative 3. So that would be negative 4 and positive 1. So this way, if you distribute all of this, we'll end up with that quadratic type exponential equation. So e to the x can be 4. And if we take the natural log of both sides, then x is natural log of 4. And using the calculator, the natural log of 4 is 1.386, so roughly about 1.1386. Now the second factor or argument, e to the x plus 1, won't work because we can't have e to the x being a negative 1, because that would mean x is the natural log of negative 1, and that doesn't work. So this expression leads us to an extraneous solution, and only this one is going to work. And then checking graphically, graphically, .386. Oh, did I write the answer down wrong? 1.386, I did. Let's go back to that. Make our key right. I put an extra 1 in there. 1.386. Y'all got to be careful. Watch me there. 1.386. In example 4, it's a similar situation. This time we're going to clear the fraction and have e to the x minus e to the negative x, and then 8 times 2 is 16. So in this case, I want to multiply the left side by e to the x, and the reason I'm doing that is to get this as a quadratic term. But whatever we do to the left, we need to do the same to the right. That gives us e to the 2x, and then this is going to be adding the powers. We'll get e to the 0, and then 16 e to the x. So we want to bring this over to the left side, and e to the 0 is just 1, So again, we have a quadratic type, but we can't factor, there are no factors of 1 that add up to negative 16, which means we're going to use the quadratic formula, but we're going to solve for e to the x because this is our variable term. So quadratic formula says the opposite of b plus or minus the square root of b squared, that would be 256, minus 4 times a is 1, and times c is negative 1. That entire thing divided by 2 times a. So e to the x is going to be 8 plus or minus the square root of 65 divided by 2 as I went along. So you can check my work that I did that right. Now, we don't know what x is, we just know that e to the x is that. So again, we're going to take the natural log of the left and the natural log of the right to be able to get x away from the power and down to where we can find some reasonable value. So x is natural log of 8 plus the square root of 65, and x is not going to be natural log of 8 minus the square root of 65. Whoop, because I believe that's going to be a negative number, not a real number, because it's going to be negative. So we'll go to the calculator, and we're wanting the natural log of 8 plus the square root of 65, and that's 2.776. And just to verify, natural log of 8 minus the square root of 65 is going to be not real. So no real solution on that portion. So, whoa, I'm losing my screen here. So this one is about 2.776, and this one is not real. So no solution on that part. And then we want to look at the graph. And in this case, I graphed the right side equation, y equals 8, and I graphed the left side of the equation, and that was the e to the x. They intersected at 2.776, 8. So we can verify that way. Example 5. Again, is this a quadratic looking thing? I see lots of natural logs there. So thinking through this, if you have the sum of two natural logs, we can rewrite that by the properties as the product of a single natural log. And then this natural log, the 2 can go back to the power. Now, this is really good because when a log is equal to a log, then the arguments are the same, so we don't need to consider those. We just need to expand. This is 3x squared minus 5x plus 2, and this side is x squared. So we use that property. The log of one side is equal to the log of the other side, then the arguments are equal. That's the property we applied right there. So bringing this x squared over, we have 2x squared minus 5x plus 2. And I believe this one factors of 2 that add up to 5. If we had 2 times 2 here, we'd have 4. And 2 times 1 would give us 2, as long as they were both negative. So one argument, 2x minus 1 is 0, when x is 1/2. And the other argument, x minus 2, is 0, when x is 2. So now let's go back and consider these two answers in the original. Now, what's going to happen when you put 3 times 1/2 minus 2? That piece is okay. what happens when you put natural log of a half minus a half? This becomes extraneous because we're taking the log of a negative number. So 1/2 is extraneous. Now for 2 works here. 2 minus 1 would be good here, and 6 minus 2 would also work. So we have one valid answer, one extraneous answer. And what does that look like in our graph? And it does hold up. That 2, 0 is our only valid solution. Now in example 6, this time we have log base 3, but we've got a number over here, so we can't use that log property. But we can say that log base 3 of x times x minus 8, I'm going to go ahead and multiply them together, that's equal to 2. And then because it's a logarithm, I can turn this into an exponential equation and say 3 to the second power has to be our number, x squared minus 8x. So I converted logarithmic form to exponential form. And x squared minus 8x equals 9. If we subtract 9, then factors of 9 that add up to -8 are -9 and +1. And setting each factor equal to 0, we can use the zero product, the law. 9 works great. That one is a valid answer. You can take the log of 9, log of 1, but -1 is not going to work in this argument, so this one is extraneous and would not be a valid solution. Now, we can use order of magnitude to compare quantities. So with your calculator, if you use your calculator to calculate the log of 3 times 10, that's log of 30, 1.477. And then 3 times 100, that would be 300. That's 2.477. And so on and so forth, 3.477, all the way up to 3 times 10 to the 10th power, that's 10.477. You see the pattern in the integer parts, how it's going from 1 to 2 to 3, and so on and so forth, all the way up to 10. And the pattern for the decimal parts are the same, 4.7712, I believe. So what are the orders of magnitude? How are they compared between 10 and 1? Well, that would be 9 times greater order of magnitude. And this is similar to how we calculate earthquake intensities. So on example, this is supposed to be example 7, isn't it? Let's change our notes here. So in example 7, we want to know how many times more severe was the 2001 earthquake in India, I'm not even going to try to pronounce that, than the 99 earthquake in Athens, Greece. So the formula says, we could compare the two. We could say R1 minus R2, using that formula, was log of A sub 1 over T plus B minus log of A sub 2 over T plus B. In this case, we could eliminate the B's. And R1 was 7.9 on the Richter scale. R2 is 5.9. So they're 2. And we've got log of A sub 1. If it's a difference, we can divide. And if we divided, the T's would go away, and we would just be comparing A sub 1 and A sub 2. So when we have log, well, hold on a minute. I want to write one more step in there. I'm going to back up a minute and rewrite this a little bit better. a sub 2 over t. So this is going to give us the log of a sub 1 over a sub 2 when we apply the properties to divide. And this base is 10, so 10 to the second power is the comparison of a sub 1 divided by a sub 2. So 10 to the second power means that the earthquake in India was 100 times greater than the earthquake in Greece. Let's write that down. So the earthquake in India was 2 magnitudes greater, was 100 times greater than the Greek earthquake. Okay, so a little bit of Richter scale. And here's one using the pH formula. So the pH formula says if we're comparing balsamic vinegar and a box of baking soda, so one's base and one's acid. So vinegar is 2.4 is negative log of a hydrogen atom, and 10 to the negative 2.4 is H plus. So the base is 10, 10 to the 2.4. We divided out the negative first. So 10 to the 2.4 on our calculator. Let's go look at that. 10 raised to the negative 2.4 power is 0.003981. So we could say, we could rewrite that as scientific notation. 3.98 times 10, is it to the negative third power? Yes, times 10 to the negative 3, and this is in moles per liter. While the soda, doing the same thing for the soda, has 8.4 for its pH, and that's negative log of the hydrogen atom. So dividing by negative, and it's 10 to the 8.4 negative power is H plus. And again, back to the calculator. 10 raised to the negative 8 4/10 power is 3.98 times 10 to the negative 9 moles per liter. 3.98 times 10 to the negative 9 moles per liter. So these are their hydrogen ion concentrations. And then how much greater is the hydrogen concentration of the vinegar than the baking soda? So we want to look at the comparison, the ratio of vinegar to soda. And the vinegar was, what was that? 10 to the negative 2.4. So we got 10 to the negative 2.4 on the vinegar, and 10 to the negative 8.4 on the soda. So this looks like 10 to the 6th power because we're subtracting exponents, and minus a negative 8.4 gives us a power of 6. So it's 6 orders of magnitude. 6 orders of magnitude difference between the two of them. And then again, looking ahead to calculus, we're going to use Newton's cooling law, which was T of T is T sub m plus T sub naught minus T sub m e to the negative kt power. And the time T sub T, that's our temperature, where is it, 150 degrees, is capital T of T. It cools to that. T sub M is our room temperature, that's 70 degrees. And T sub 0 is the amount we're starting with. So we're taking it out of the oven at 375 degrees when it comes out. And we're putting it in a room that's 70 degrees. And we want it to cool for 20 minutes time. So T is going to be negative 20 K. And at first we need to find the value for K. So 150 minus 70 gives us 80, and 375 minus 70 gives us 305, e to the negative 20k. So if we divide by 305, we can take the natural log of the left and the natural log of the right and get the 20k out of the exponent. And that would help us to find the k value. So we're dividing by negative 20, and that's giving us our k. So we're going to go check that on the calculator. And we're looking for natural log of 80 divided by 305. And then that entire thing divided by negative 20 for our constant of variation. So that would be k, is about 0.066914, if I remembered that right. 66, yes, okay. So now we know our constant, and we want to solve for, we're looking for T of T. When is that equal to 90? So again, using the formula, capital T of T is 90 when our original temperature is 70 plus, what did we have, 305 was the difference, e to the negative k times T. And we're solving for T this time. So 90 minus 70 leaves us with 20. And we've got 305 e to that k T power. So divide 20 by 305. And we want to take the natural log of that. And if we take the natural log of this, we'll get the 0.066914 T. And then we can do natural log of 20 over 305 divided by that 0.066914. And that's going to give us the T value. So back to the calculator. We got natural log of 20 divided by 305, and that entire amount divided by negative 0.066914. So about 41 minutes, since the time is 40.7176. So it takes about 41 minutes before the brownies will cool to 90 degrees Fahrenheit. And then you got a nice cold glass of milk and ready to do math homework. So until next time, take care.